Okay, good morning. Or good afternoon or good evening. Sorry, I'm filming this in the morning. Today we're going to be talking about section 8.2. Okay, our first objective is we want to be able to calculate the numerical value of a sample proportion, which we've been doing all along. Okay, and the other thing is we want to be able to check our conditions for a confidence interval. All right, so we know that proportions can be expressed as a percentage, a decimal, or a fraction. We really don't usually write our answers as percentages. We usually write them as the decimals. Okay, our notations we know. P is our population proportion. P hat is our sample proportion, where it's x over n. Okay, so if you want to write it as p hat equals x over n, so visually it's a little easier for you to use. All right, x is our number of successes, and n is our sample size. Just like in the last chapter with sampling distributions where P and Q added up to 1. Well, now we have P hat and Q hat also add up to 1. You're never going to mix and match, all right? But you'll have, so P and Q always add up to 1, and P hat and Q hat always add up to 1. So sometimes you'll see it written as 1 minus P hat. Sometimes you'll just see it as Q hat. Just like with our sampling distributions where we had conditions to check, in the sampling distributions, we had to check our large counts and our 10% condition, okay? So this time we're also going to be adding in that we need to make sure that our data was collected using a well-designed random sample or randomized experiment. From here out for the rest of the year, we need to make sure that our data was collected randomly. That's incredibly important, okay? Because we need to make sure without randomness, there's probably going to be a lot of bias in the results, okay, a large level of bias. A couple other important things to note. For our large counts, we need it to be n times p hat and n times q hat are greater than 10, all right? If these pass, then that means it's okay to use the normal curve, just like last time. Last time it was n times p, n times q. For these, it's n times p hat, n times q hat. We also need to check, is our population at least 10 times our sample size? That means it's okay to use the standard deviation. Now, instead of using the standard deviation, we're going to use something that's called the standard error of p hat. Okay, I have it actually on the next page. I put them in a little bit of a silly order. So on the next page, all right, I should have put these in a different order. And I made a note, you might want to just take a look at in your textbook on page 496. Okay, so page 496 does a really nice job explaining the difference between standard deviation and standard error. So the standard error of your sampling distribution or your sample proportion, we're going to call it SE of p hat. It's going to work the same as a standard deviation. Okay, put it here. Your standard error is the estimate of the standard deviation. It describes how close the sample proportion p hat will typically be to the population proportion p in repeated simple random samples of size n. So if you're working on a sampling distribution, then you have sigma sub p hat and you use p and q. If you're working on a confidence interval, all right, and we've got a sample proportion, then we're going to work with p hat and q hat in the numerator. All right, but they're going to represent the same basic idea. So we would say it's okay to use the standard error of p hat equals our formula. Okay, so this is something that, this is something that you guys, a lot of people got what they're good for backwards on your chapter 7 test. Like you knew to check stuff, but you didn't know like what you were actually getting out of that check. So this is something that's concrete and it's here for the rest of the year. Like every section has, you've got to check your conditions, all right? So you have to make sure that when you're checking your conditions, you know what you're finding. This is just so critical. All right, so Mrs. Quinn's class wants to construct a confidence interval for the proportion P of pennies that are more than 10 years old in a collection of 102 pennies. So they got a collection of 102 pennies. Their sample had 57 pennies that were more than 10 years old and 45 that were at most 10 years old. We want to check the conditions for constructing a confidence interval for P that are met. We're just checking the conditions. So random, it actually doesn't say that it's random. It just says it's a sample. So this one we actually fail, okay, because it doesn't say that they collected them randomly. All right, just think about it. If you just collect pennies from your wallet, it might not be, like 5 people's wallets or piggy banks or whatever. It might not actually be a random sample. Okay, you might have gotten them all at the same time, or from the same roll of pennies from the bank, or whatever it would be. All right, we need to identify what p hat is. P hat, we're looking for the number of pennies that are more than 10 years old. So that was 57 out of 102. Okay, where n is 102. So when we check, we need to say 102 times 57 out of 102 is 57. 57 is at least 10. And then we're going to have 102 times, the rest are 45 out of 102. Okay, so that'll be 45 is greater than 10, and we're good to go there. This means what? This means okay to use the normal curve. So whatever notes you need to take to yourself, take them. All right, and our population, all pennies. Yes, of course, there are millions of pennies out there, okay? So are all pennies greater than 10 times 102? Yes, absolutely, that's reasonable. And this lets us use the standard deviation later, okay? So yes, so actually, no, we wouldn't be able to do a confidence interval because it doesn't say that it's random, but we're going to proceed as if it is. Okay. We talked about standard error here already and standard deviation. So now what we need to do is we need to talk about, all right, like how do we do the math? How do we do the confidence interval and come up with the numbers? So the first thing we need to talk about is we need to talk about how to find the critical value. So here's the formula that's on your formula card that we went over actually in section 8.1, okay, where it's your statistic plus or minus your critical value times your standard error of your statistic. This is this formula we just did, okay? So these go together and these go together, your statistic. So what we need to do up here in example 2 is we need to figure out this critical value, this z star, okay? And to do that, we're going to use our z chart. And in last lesson, I had gone through, there's like 3 main confidence levels, right? 90%, 95, 99. I'll also chat with you about how to find 80%. Right? Table A is your normal curve table. All right, I'm going to just use technology, norm CDF all the way. Actually, we need to use inverse norm. But yeah, we're going to use our normal curve. So here's what it's going to look like. If you have a normal curve, an 80% confidence interval from your mean goes down 40% and up 40%. It's the middle 80%, okay? Your Z star is the number, like this would be your Z star here, and this would be the negative of the Z star. Okay, they're gonna be the same number, just one's the positive, one's the negative, which you don't actually really need to worry about because your formula counts for the fact that one's a positive and one's a negative. Okay, the one on the right's the positive, the one on the left's the negative. So you just need to remember how to get your values, right? If you want to do inverse norm for this number, we would need to do inverse norm of 0.1, right? Because if here's your mean, 50%, if that's 40, inverse norm always goes area from negative infinity up to the line. So this one would be inverse norm of 0.1. This one here would actually be inverse norm of 0.9. Do you see how 10, 40, 40, 0.9 would get us this number? So right now, test on your calculator, inverse norm of 0.1, inverse norm of 0.9, they would give us Z stars of 1.28. Okay, so if you have 90% confidence interval, then that means that it's the middle 90%, which means you've got 45 here and 45 here. So the Z star, to get this one would be 0.05 for your inverse norm area. And to get this one, you would have 0.95. Okay, so every time for proportions, they're always going to be the same numbers. So every time you have a 90% confidence interval, your Z star is equal to 1.645. 95% confidence interval. All right, you can figure out, right, take 95, cut it in half, you're going to get 0.475 and 0.475. Your z-stars for 95% confidence interval, 4 proportions, will always be 1.96. And 99, you would have 0.495, 0.495 here for your areas. Be careful, that would be 0.005 for this tail. And a 99% confidence interval is always going to give you a z-star of 2.575. All right, so one choice is to just memorize these. The other choice is to like do inverse norm every single time. You will naturally just memorize them as you do all of your practice problems. As you do your practice problems, these just kind of come together for you. So depending on what the confidence level is given to you in the problem, tells you which one to use. You're only going to use one. So like if I give you a scenario and I say the 95% confidence interval, then you're going to use z-star equals 1.96 right here. If I had said find the 99% confidence interval, then you would use the 2.575 right here. Okay? So if we take a look, let's go back to that penny problem. Right? And as you're getting the hang of it, if I were you guys, I would just like jot down the formula, maybe even throw it on a Post-it note or something. I mean, it's not on your formula card because it's, this is what's on your, oh, it's not there. It's single-sided. This is what's on your formula card, and this is separately on your formula card. But you need to know how to piece it together. So we want to go back to that penny example, right? We already checked our conditions. We're going to proceed as if it was actually random so that we would meet our conditions. And we would have p hat, we had said, was 57 out of 102. Okay, we want to calculate and interpret the 99% confidence interval for p equaling the true proportion of pennies from the collection that are more than 10 years old. So what we're going to do, 57 out of 102, I'm going to put 0.559. I divided it down. You should go at least 3 decimal places for any kind of fraction that you're dividing out. Okay, so we're going to have p hat 0.559 plus or minus the z-star is 2.576. Did I just give you 575, 576? We'll go over it. We'll like chat. It should be 2.576. I'm sorry. I think I rounded wrong on the last one. Maybe you caught it for me. Then in here, we're going to have 0.559, 0.441, and 102. Okay. You're going to type this twice in your calculator or just go up and bring it down. You know, we've practiced. So you're going to go through this twice, once for the positive and once for the negative. 0.559 minus is going to be the left-hand side of your interval, and then the 0.559 plus is going to be the right-hand side of your interval. Your answer comes up to be 0.432, comma 0.686. All right, remember, at least 3 decimal places, guys. And what does this mean? This means that we are 9, because remember, it says calculate and interpret. If you forget to interpret, half off every time, right? You're missing half the problem. We are, Marshall, no, 99% confident that the true proportion of pennies older than 10 years is between 43.2% and 68.6%. All right. Now, part B is saying, is it plausible that exactly 60% of the pennies in the collection are more than 10 years old? Explain. So I would say, so think about it, like, does it make sense? Like if, let's say that she had this huge bucket of pennies, right? And she picked 102 out of there as a sample, all right? And then 57 were older than 10 years, right? Then would it make sense to say, okay, that is it plausible to say that exactly 60% of all the pennies are in there? I'd say yes, it is. Okay? So first, answer the question. Since 0.6 is included in the interval, it is plausible. Okay, 60% is contained within this interval, so it would be a plausible, possible answer. All right. Now, what we need to do is when you have to do a confidence interval problem, you need to do all of these pieces together. Okay, you have to identify your conditions. You need to state what you're looking for, check your conditions, do the work, and then interpret your problem. Okay, so what we're going to use, there's two big acronyms that we use a lot this year. All right, and for confidence intervals, we're always going to use panic squared, right? And you're less likely to panic about the math if you know how to panic squared for statistics. So you're going to use this acronym, and if you hit all of these pieces, then you will get full credit on every problem. The problem is not going to hold your hand and tell you to do all of these pieces. However, you are expected to do all of these pieces. So like here, it says in her first grade social studies class, Jordan learned that 70% of the Earth's water surface was covered in water. She wondered if this was really true and asked her dad for help. To investigate, he tossed an inflatable globe to her 50 times, being careful to spin the globe each time. When she caught it, he recorded where her right index finger was pointing. In 50 tosses, her finger was pointing to water 33 times. Construct and interpret a 95% confidence interval for the proportion of the Earth's surface that is covered in water. All right. So what we're looking for, notice it doesn't say check your conditions, but if you don't check your conditions, it's wrong. Okay. We're trying to figure out here, is P equal to 0.70? That's like the ultimate question, right? Is that a good approximation? To do that, we need P hat. P hat is our proportion of times from the sample. The sample size was 50 tosses, and 33 of them were pointing to water. So our P hat is 0.66. Okay, now you're going to need to write a little tight, okay, because this is a small space, and I'm sorry. So first we need to identify our parameter of interest, and it's okay to just use this checklist to get through, okay? Our parameter of interest is our our population that we want to find. So we want to estimate P equaling the true proportion of Earth's surface that is covered in water. Okay, you need to restate what we're actually trying to estimate. Our assumptions are our conditions. It just doesn't work nice if I say like P, C, N, I, C. Okay, so assumptions and conditions can be interchanged. That's the random, large counts, and 10% condition. So random, all right, the points were determined randomly by the spinning and the tossing, right? That's good. All right, our large counts. We need to check, is n times p hat at least 10, and is n times q hat at least 10. All right, so is 50 times 0.66, that's 33, good, that's at least 10. And then we're gonna have 50 times 0.34, that's gonna give us 17, is at least 10, we're good there. Okay, so you need to show your work. Okay, that means what? It's okay to use the normal approximation. Okay. then we need to do our 10% condition. Which is our population at least 10 times our sample size? Well, we tossed it 50 times. So is it at least 500? Well, yeah, because this is limitless, right? All tosses is an infinite. He could toss this an infinite number of times. Okay. So that these three pieces, 1, 2, 3, are our assumptions. The name of our interval, right now we only have one name. We're going to wind up with, I think, 8 different confidence intervals this year. So eventually you'll have a lot of names, but right now we've just got one. Okay, we call it a one sample Z interval for a proportion. You can't abbreviate it any shorter than that, guys. This is its name. It's a one sample Z interval for a proportion. Now I'm going to come over here to finish the rest. I is the actual interval, all right, where we do P hat plus or minus Z star. We have a 95% confidence interval, which means our Z star is a 1.95 square root 0.66 times 0.34 over 50. Note, we're not using the 70 that we're estimating at all. We're trying to see, does 70 land in here with the sample proportions? We're not using the population that we're estimating, like trying to see is it true or not. Okay, we're using just the sample stuff that we found. We get an answer of 0.529, 0.529 to 0.791 for our interval. Notice the math is just one of the 5 steps. And then C squared is we need to state a conclusion in the context of the problem. Okay, so we are 95% confident. You could write certain or sure, okay, but you need to say how certain or sure we are. We are 95% certain that the true proportion of the Earth's surface covered by water is between 52.9% and 79.1%. Okay, good job. I know there's still one more page of this section, but I think we've gone too long already as is. So we will actually do, please just remind me, I know you guys will remind me, just remind me, we'll do those 2 problems together in class. All right, good job today.